Now let's see this question. This question came in GATE 2016 for 1 mark. The question is, assume that the algorithms considered here sort the input sequences in ascending order. So these 4 algorithms are given here: quick sort, bubble sort, merge sort and insertion sort. If the input is already in ascending order, which means that whatever input is being provided to these sorting algorithms, they are already in ascending order, then which of the following statements are correct? Okay, so let's start with first statement. The first statement is quick sort runs, so we have to find the true statements, right? So if a input is already sorted, something like 1 2 3, let's say 4 5 6 7 8, okay, this already sorted input is fed to the quicksort algorithm, then what is the running time? That we have to find out. Okay, so let's say that we are choosing the first element as the pivot. Then what is going to happen? All the elements rest of the elements will come towards the right and nothing will come towards the left. Why? Because 1 is the minimum element, right? So this entire sublist will come on one side. Now after that we will again run quicksort recursively on this part. Again, if we take the first element, then this element 2 is the smallest in this list, and therefore if we choose this as the pivot, then all the other elements will lie towards one side. Okay, so we are seeing here that what is happening is that our pivot should be chosen such that it divides the algorithm, it divides the entire list into somewhat equal parts, but that happens in an average case for a random input. But if the input is already sorted and we do something like that, then our recursive function will be something like this, that Tn is equal to Tn minus 1. Why? Because there is only one side we have to do recursion, and that has n minus 1 elements, okay, plus c. If we solve this, then this will come out to be theta n square. So this statement is correct. Okay, now we'll see bubble sort in the end. Firstly, let's see merge sort. So it's the same sort of input, which is a sorted input. Let's say this 1 2 3 4 5 6 7 8. If this is fed into merge sort, then what is going to happen? In merge sort, what we do? We firstly divide the list into 2 parts. So let's say this is the division. After that, we recursively sort this part and then merge them, right? So how we solve recursively this part? Again, we will split this into 2 parts, okay, and this right side also we will split into 2 parts, and then recursively we will merge this. Now you understand that even if 1 2 3 4 is sorted and 5 6 7 8 is sorted, but then when we are going to merge it, then again it is going to be taking theta n time. Why? Because two-way merging, how it happens, that you know that first element is compared with this, so the minimum among these two is chosen. So in that fashion, how the two-way merging algorithm works, in that way again the time taken will be theta n. So we are readily seeing here that the time taken is going to be same as even if it is not sorted. My point is that the recursive function will be Tn is equal to 2 times Tn by 2 divide 2 times n by 2 plus theta n. Okay, same as any other input. So the recursive function is not going to be different even if the input is sorted. So here the on solving this recursive function, we will get theta n log n, which is same as even if the input is not sorted. But even if the input is sorted, we are getting theta n log n, and it is saying that it is taking theta n time, which is false. So this statement is false. Now let's talk about insertion sort. So in insertion sort, see, if we are having an input like which is sorted, let's say 1 2 3 4 5 6 7 8, this input again, then In insertion sort, how we approach? So we take the first element, it is already in sorted order, so we don't do anything. After that we start with the second element and we insert it at the proper position in the sorted list. 2 is greater than 1, so this part is already sorted. Then we pick the third element and we insert it in the proper place. But again, whatever is the highest element, 2 in the previously sorted list, 3 is higher than the highest in the sorted list. So again 3 position is okay. So what we are understanding here is that generally what happens, that we go all the back to the end and we try to find out actually what is the proper place, and in worst case we might have to go all the way to the beginning. So at the kth element, for the kth element, all the k minus 1 elements have to be scanned and then the proper insertion happens, right? But here we don't do that scanning and we initially only come to know that that is the proper position just by comparing it with the maximum element. The first comparison only we come to know that it is the proper place, so we don't have to do anything because it is already sorted. So in that sense, what my point is that earlier the number of steps which used to be, so if it is not sorted, the number of steps was something like theta of 1 plus 2 plus 3 all the way till n minus 1, right? So last element we have to scan through all the n minus 1 element to find the proper place to insert. It is the situation when the input is not already inserted. Input can be anything. So in that case you all know that it is theta n square. But in our case what happens, that number of steps here will be actually less. Here the number of steps will be actually, we are just seeing that okay, just in constant time we are able to find that okay, this is only the proper place. Again for the next comparison also we are seeing that this is the proper place. So actually we are taking constant number of constant amount of time. How many times? N minus 1 times, from the second element to the nth element. So n minus 1 times, so it comes out to be theta n. So in this case insertion sort runs in theta n time if the input is already sorted. So this statement is correct. Now let's see bubble sort. So okay, so in bubble sort I will explain it here. So in bubble sort, if let's say we are considering something, a sorted input something like this, 1 2 3 4 5 6 7 8. Okay, now what we do in bubble sort is that we compare the adjacent elements, okay, and if this element, the other element, the element on the higher index, if that is smaller than the previous element, then we swap. Okay, so if it would have been 2 first and then 1, then we would have swapped. Okay, so firstly I will show you with an example other than the sorted one, and then we will come out to this sorted input. Firstly let's consider another input which is not sorted. Let's say something like 1 2 3 4 6 8 5 7, just any input which is not already in sorted order. So how we are going to do here? What we will do that, see, there is nothing to swap here because 1 is smaller than 2 all the way till 4 is smaller than 6. Okay, 6 is smaller than 8. Okay, here see, 8 is bigger than 5, so we basically swap these two elements. Okay, so in the next iteration what is going to happen? We are going to have something like 1 2 3 4 6, and this will be swapped, right? So 5 will come here and 8 will come here, right? And 7 will be here only. Again what will happen? Again we are seeing that 8 is bigger than 7, so again we will swap here also. So after swapping, after this swapping, what will happen? The next time we are getting the list something like 1 2 3 4 6 5 7 and 8. So what is happening at the end of this, that the biggest elements gets bubbled up to the rightmost position. Okay, and we then say that okay, this is at the proper position. Now for the rest of the elements we have to do that same thing again. That is how it works, right? So for the rest of the elements, let's try to do one more time. So here we see that 1 is smaller than 2, smaller than 3, smaller than 4, it is okay. 4 is smaller than 6, okay. So the problem is happening at the place 6 and 5. So we are seeing that this should be swapped, then we will get 1, 2, 3, 4, 5, 6, 7, and then here 8 is already fixed, not a problem. But 6 is smaller than 7, so nothing to do. So again, whatever element is coming to the final end, that is the final element. Okay, so these two are settled. Now we have to again do the algorithm for the rest. So when just note here that when we are doing that bubble sort on again this part, then again we are doing that only comparing this with this with this with this, 4 with 5, and we are seeing that nothing is going to change, and that's why we say that in the next iteration this 6 is settled, and we do this all the way till the end. But my point is, why we are doing this again and again even if this list is already sorted? See this list, 1 2 3 4 5 6, this is already sorted, but as per the bubble sort we actually do again on this sublist also. But here at this part only, after these two iterations, this part was done, and after that there is nothing to do here. But then also we do that, we do our process of bubble sort again and again, and that in turns out that n minus 1 swaps are happening one time, and n minus 2 swaps are happening the second time. Like for the first, when 8 was settled, then actually n minus 1 swaps overall were happening, right? So n elements are there and we are comparing adjacent, so n minus 1 swaps were happening. But when the second element is settled, second from the rightmost, that is settled, then n minus 2 swaps were happening, right? And then similarly n minus 3 swaps will happen. So similarly, what my point is that the overall running time as per the conventional bubble sort will be something like theta of n minus 1 plus n minus 2 all the way till, let's say, 1. Okay, so my point is that this is going to be something like theta n square. Okay, but see here, they're also saying that bubble sort runs in theta n square time. So this should also be true, right? So our answer will then be 1, 2 and 4. But see, in the options there is nowhere 1, 2 and 4. So actually we have to think more, but the problem is coming because actually bubble sort algorithm, there is an optimized version of bubble sort algorithm. This might be confusing, those who are not knowing, but then what happens is that there is an optimized version of bubble sort algorithm, and they are talking about that optimized version even if they are not mentioning it. Okay, they have left it up to you to understand that. But what happens that in a particular optimized version of bubble sort, once we have a situation something like this, let's say, see, we are comparing these two, and we are seeing that whether we have done any swaps or not. So what happens that if we see that in a particular iteration no swaps are happening, then we can safely say that the entire that list, the sublist, is already sorted, and after that going again for n minus 3, and like after n minus 3 n minus 4, n minus 5, so going all the way till the beginning, that which is giving us the theta n square time, we will stop there only, and we will exit the bubble sort algorithm, and we will say that okay, the sorting process is done. Okay, if we do that optimized version, then if the input is already sorted, then actually it is not going to take theta n square time. You are understanding, right? Why? Because as I mentioned earlier, that if the input is already sorted, then we will just compare 1 and 2 and we will see that nothing to swap. 2 and 3, 2 is smaller than 3, 2 is not bigger than 3, that's why nothing to swap. Similarly, we will see all the adjacent elements and we will see that there is nothing to swap, and in just one round only, in just n minus 1 comparisons, we are coming to know that there is nothing to swap. And once we know that there is nothing to swap, in the optimized version what happens that we simply exit the bubble sort algorithm. Okay, as simple as that, because this is already sorted. We have confirmed that this is already sorted, and that's why we will not do anything. And if we implement that optimized version, then it is simply n minus 1 swaps, which is basically theta n time. So they are talking about that. So bubble sort runs in theta n square time for the sorted algorithm, for the sorted input, is actually wrong. Okay, so if 1 to 4 would have been some option, then it's okay, but here they are not having that option. So actually it is coming out to be that this bubble sort is an optimized version, and therefore this is also wrong with respect to the options, and that's why 1 and 4, they are only correct, and therefore our answer is D.